All right, then I will hand over to Eduardo to introduce today's speaker.
Thank you. Shh. Is it on? Yeah. Hi, everyone. It is my great pleasure to introduce the speaker today, Max Pettini. Max Pettini started his career in London, at UCL. Then he moved for a few years to Australia, then went back to the UK to be a professor at the Institute of Astronomy in Cambridge, where he is now. His research focuses on high-redshift galaxies and the intergalactic medium, has received many, many awards, like the Herschel Medal, and most recently the Gruber Cosmology Prize this year. And I'm going to quote why he got this award. So it was for bringing the light element abundances and Big Bang nucleosynthesis into the realm of precision cosmology, which sounds extremely important. And I think that's what you're going to be presenting today. And we are all very excited to hear about the deuterium. So take it away, please.
Okay, now it's fine? Good. Yep, the light is on, yeah. Good afternoon, everyone. Thank you for coming, and thank you for the invitation to speak at this prestigious colloquium. It's always a pleasure to visit your beautiful city and to experience firsthand this vibrant scientific atmosphere of Heidelberg. I've talked to so many interesting people today. In just 4 hours, my head is buzzing with all the wonderful things I've heard. Is this better? Okie dokie. So, the first thing I want to say in my talk is that it's really a joint talk. Although I'm the only one here, this work has been carried out in Italy in collaboration with Ryan Cook, who was a PhD student at the Institute of Astronomy and is now a professor in Durham. And it's about Big Bang nucleosynthesis, if any of you have read the abstract. So what first attracted me to this topic in astrophysics is the fact that it's the only way we have, observationally, to probe the very first few minutes in the life of our history, of our universe. The process stick here. So we're talking about this period here, where the light elements were synthesized, and that is 400,000 years before the curtain was finally lifted when the cosmic microwave background was emitted. The ideas, I'll give you a brief historical background. The ideas of BBN stem back to the years after the Second World War, where George Gamow, his PhD student, Ralph Alpher, and Robert Herman, together they worked out that if there was an initial fireball, if there was an early stages in the universe where the temperatures and the densities were sufficiently high, protons and neutrons would combine to form heavier elements of the periodic table. So we go back some 75 years to the seeds of these first ideas. But the seeds lay dormant for about 20-25 years until the cosmic microwave background was discovered in 1964-65. And at that point, the confirmation that there had been a Big Bang immediately produced a number of papers that explore the consequences, including BBN. Jim Peebles wrote a paper in 1965 and 66, and then Robert Wagner, when he was a PhD student at Caltech, working for Fred Hoyle, believe it or not, he put the first quantitative calculations of the Big Bang, the reactions of the Big Bang. And in fact, the figure number 1 of this paper here is not very different. It's pretty much the same as a modern version of that figure, which explains the reactions of BBN. The only difference between the 1967 paper and now is that the 1967 paper was in black and white, because we couldn't print color pictures in journals then. And As far as we need to know for this talk, essentially, all the neutrons that combine with protons end up at the end of BBN included in helium-4. They all end up in helium-4 here until the universe expansion lowers the density and the temperature to the point where these reactions are no longer viable. Small amounts are left in these other isotopes on the way to forming helium-4. That's primordial nucleosynthesis. Very smaller amounts are left as deuterium, heavy hydrogen, H2, helium-3, and lithium-7. And exactly how much is left in these trace amounts depends on this parameter eta on the x-axis here, which is the baryon to photon ratio. And because we know the photon densities through the exact black-bodied spectrum of the CMB, of the cosmic microwave background, we can turn these element abundances directly into values of the fraction of the critical density contributed by baryons, by ordinary matter, times the Hubble constant squared in units of 100 kilometers per second per megapascal. That's what little h is here. It was David Schramm, who is still much missed today, Michael Turner from Chicago, who pointed out that deuterium is actually the element, other the ones made out of the Big Bang, that is most sensitive to this omega baryon. It's the baryometer of choice. It has a steep dependence on omega baryon. So the reality is that if we can measure deuterium or any of the other primordial elements with sufficient precision, we can actually weigh the whole universe, at least in baryons, in ordinary matter. It's a very powerful tool in that respect. The first time, to my knowledge, the deuterium was detected was actually in the local interstellar medium. It was one of the first results published, made possible by the Copernicus satellite in the 1970s. That's the satellite that really opened the doors to UV astronomy, which didn't exist before. Look how good referees and editors were then. Received 21st September, revised 18, published a couple of months later. Don York and his collaborator, John Robertson, Don York is now also Chicago, recognized this, recorded the spectrum of this nearby star, beta Cen. It's only 120 parsecs away. It's very bright. They recorded the spectrum, the UV wavelengths. Look at the x-axis here, 970 angstroms. We're in the far UV. This is a Lyman gamma of hydrogen in the star and in interstellar medium blended together. They recognized this little blip here, this almost insignificant absorption feature here, as the deuterium Lyman gamma line. And that's how we detect deuterium. It produces an isotope shift that is easy to see. If you look at the Lyman series of hydrogen, all the transitions from the ground state up to higher excited levels, they produce the Lyman alpha, Lyman beta, and so on series. And of course, deuterium has the same transitions, but because of the extra neutron in the nucleus, those energy levels are all shifted to slightly higher energy levels, and that means the absorption lines from deuterium are a shorter wavelength. It takes a bit more energy to reach those levels, are a shorter wavelength. There's the blue shift, which in velocity terms corresponds to 82 kilometers per second. And it's the largest isotope shift of any of the other elements in the periodic table. Normally, isotope shifts are a few kilometers or fraction of a kilometer per second. This is 82. So returning back for a moment to this Copernicus measurement in the 1970s, all we could get from it at the time was an upper limit on omega baryon. And the reason is that whenever gas is turned into stars, deuterium is destroyed, is burnt. So all of the deuterium that exists today was created in those first 3 minutes of the history of our universe, and subsequent cycles of star formation that burnt some of that deuterium. Of course, whenever you form stars, you also make heavier elements of the periodic table that astronomers, much to the confusion of physicists, all bunch together and call them metals. And so, if you, with that initial measurement in the local interstellar medium, all we have is some of the some of the deuterium that was made in the Big Bang. To go from that to how much was made in the Big Bang requires a correction, and that correction is quite uncertain. You can do it, but then there are your result has a large uncertainty, and that's not very useful in today's era of precision cosmology. So how do we measure the primordial abundance of deuterium rather than what's left today? The straightforward answer is we look for absorption lines in near pristine gas clouds in the distant universe. And I'll explain that a little better. It would be known to some of you at least that when we look at a distant object, if it's a quasar or a galaxy or a gamma ray burst, in this example of the quasar, we sample everything along the line of sight from the quasar to the Earth. And how we sample it is in the spectrum of the quasar, we see all these absorption features, and they're mostly hydrogen absorption lines produced by mostly by the intergalactic medium in the line of sight between the quasar and us. This is this principle of quasar absorption line spectroscopy. In a really prescient paper written in 1976, Thomas Adams, and I've tried hard to find a picture of him, but I haven't been able to. He was also from Chicago, so this is the third time the University of Chicago comes into this talk. He pointed out that it is shown that in suitable clouds, the deuterium Lyman alpha line should be detectable. And he encouraged observers to look for this feature, since its detection would have important cosmological implications. This was a really prescient paper in 1976, because we had to wait 20 years before this became possible. And we just, in 1976, we didn't have the means to make this measurement. This means became available with 8 to 10 meter telescopes. Here, the Keck telescopes that produced the first measurement of deuterium in high redshift systems. So, the first paper was published in Nature by a good colleague of mine, David Teitler, and his collaborators. And here's the data. They looked at this cloud, which is metal poor, only 100th or so of solar, at a redshift of 3.57, looking back from 10, 12 giga years. These are the lines in the Lyman series, from Lyman alpha at the top to Lyman 13 that is shown here. And you can see the deuterium absorption on the blue wing certainly in Lyman alpha, and possibly there in Lyman beta as well. From this data, Teitler and collaborators concluded they could measure an abundance of deuterium of 2.3 times 10 to the minus 5 with an uncertainty, an error of about 25%, as you can see here. So this is the first measurement that I know of the primordial abundance of deuterium. There are essentially very fewer metals in this cloud, and so we can be confident that this is the primordial value. But to get from here to 1% precision, which is what we're interested in achieving in this day, it requires a somewhat different approach. Let's look back at these quasar absorption line cartoon, if you like, but it is a real spectrum. All of these lines, they're all hydrogen lines. They all have the deuterium counterpart. But if you remember one of the earlier figures, we expect a few times 10 to the minus 5 in deuterium compared to hydrogen. So the deuterium absorption will not be seen in most of these lines. Their column density is too low. We need to go to this heavy weight to be able to see it at all. So if we plot the column density distribution, you can think of it in terms of mass of each of the structures that are producing its individual absorption lines at different redshifts between the quasar and us. We have a distribution like this. This spans 10 orders of magnitude. On the y-axis is number of lines. On the x-axis here is column density. You can think of it in terms of the mass, if you like. And it goes from little wisps of gas in the IGM, in the intergalactic medium. These lines appear, many more of them, by 15 orders of magnitude, than the heavyweights at the other end of the distribution. Those heavyweights have a very characteristic shape, shown on the top here, and they were first identified as a particularly interesting class of quasar absorbers by Art Wolf, who pointed out that probably galaxies selected by neutral hydrogen absorption. And a lot of the credit to pushing the research on these Dampier alpha systems really goes quite rightly to Art Wolf. Now, if we look at these Dampier alpha systems in their metallicity, we have also distribution of values. Some of them are as metal-rich as the Sun or the Orion Nebula today, and most of them are metal-poor by a factor of 20 or 30. That's the peak of this distribution. And we're looking at galaxies at an earlier time. It's reasonable to assume there's been less chemical evolution. But there's a tail at the low metallicity end that stretches to almost 1,000th of solar. In fact, beyond 1,000th of solar today. We know this plot is quite old now. We now know tens of thousands of confirmed or candidate Dampier alpha systems. There's a large body of data thanks to surveys like the SDSS, for example, the Sloan Digital Sky Survey, and subsequent large-scale surveys. So it is these most metal-poor of DLAs that turn out to be the astrophysical environment where we can best measure with high precision the primordial abundance of deuterium. The first reason is obvious. Whenever gas turns into stars, deuterium is burnt. And the metals are made up, are produced. So if we look at environments where there are very few metals, that's where we can recover the primordial abundance of deuterium. I've already said that. So that's the first point. The second point is that it turns out that these most metal-poor or Dampier alpha systems also have the narrowest absorption line. Here's an example. At the top here we have the usual telephone number of this particular quasar. It has one of these DLAs. You can see it at the top. It's easy to get an accurate measure of the column density of hydrogen from those extended wings on the Lambda alpha line. In this case, it's 2.5 times 10 to the 20 atoms per square centimeter. And here are various metal lines at the same redshift as the hydrogen line, and they tend to be rather weak. In fact, from these ion lines here, we deduce a ion abundance of about 1/200th of solar. But you can see something else. If you look at the x-axis here, these are kilometers per second. These lines are a few kilometers per second wide. And we're looking for a shift to -82 in deuterium. So these are ideal physical conditions to resolve clearly this isotope shift to C deuterium. Why are they so narrow? Well, if there's anything like a mass metallicity relation, then these structures with such low metallicity, with such low element abundances, probably are fairly low mass systems in terms of the overall potential world in which this gas finds itself. perhaps equivalent to dwarf galaxies in the local group, which have the same metallicities, the same internal velocity dispersion, and many other parameters comparable to that. So we could be seeing in some of these most metal-poor DLAs high redshift counterparts to the dwarf spheroidals or dwarf galaxies more generally in the local group that have been studied so extensively. So the second point then is, as I said, that the narrow absorption lines make it possible to resolve this 2 kilometers per second isotope shift between deuterium and hydrogen very well. The third point is that with such high column density systems, now we have detectable deuterium lines not only in the first 1 or 2 lines in the Lyman series, but in lots and lots of lines in the Lyman series. So here's an example, another quasar, redshift 3.07 or so. Its ion abundance is nearly 1,000th of solar. That is its column density, well determined again from the wings of this line. And now here is a montage of all the Lyman series lines along this line of sight. Lyman alpha and Lyman beta are so strong that you lose the deuterium component. The hydrogen is in red with red ticks, and the deuterium is with the green ticks. So we see deuterium Lyman gamma, Lyman delta, Lyman epsilon, Lyman 6, Lyman 7, Lyman 8, Lyman 9, 10, 11, 12, 13, 14. I think we stop at this point because when you get to I don't know, also 15, and then beyond 15, the line. Remember how these energy levels work. As you go higher and higher up the scale, as you were, the lines get closer and closer together, and so they finally get merged at Lyman 16, and the transitions are less and less likely. The most likely one is Lyman alpha. As you go higher the atomic structure, the transitions are less likely, and that's why his deuterium line and the hydrogen line gets weaker and weaker as you go further up. But look, we have from Lyman gamma to Lyman 15 in 12, 13 independent measures of the deuterium to hydrogen ratio. Much more accurate assessment of this quantity than was possible, for example, for David Tytler's system. So we have these 3 things. We have the low metallicity, we have the narrow lines, and we have a wealth of information along a single sight line to be able to measure the abundance with the precision of deuterium with the precision that we want. If I made this sound very simple, believe me, it's actually a very delicate experiment. I don't know if you remember this Dampler from the previous slide. The Dampler-Alpha systems are at the high column density end of the distribution of column densities of the absorbers. They're the rarest. They're the heavyweights, but the rarest by 15 orders of magnitude compared to the very piddly little lines in the IgM. And if you remember the distribution of metallicities, the lowest metallicity ones are also the tail of the distribution. So there's few systems that we know about that satisfy all the conditions required. Furthermore, that's not the only thing. We need to find them in front of a quasar that's bright enough to perform high resolution spectroscopy with high signal to noise ratio. So there's a cutoff in the magnitude that we can access. There's a cutoff in the redshift. We have the redshift of the quasar and the redshift of the absorber had to be in a window where we can actually access that spectral region with minimum confusion. So everything has to come just right. And when you found, after sifting through thousands of these, hundreds, a few highly suitable cases, then each observation requires at least 30,000 cycles of integration on a high resolution spectrograph, either on the VLT, on Keck, either on UVES or high res. 30,000 seconds of clear skies. That's not, you've got to take into account poor seeing and cloud and so on. The final thing is that we have developed specifically we being mostly Ryan Cook, developed specific analysis tools that allows to take into account both the random and systematic errors in extracting the final number that we want, the deuterium to hydrogen abundance. The systematic here are exactly where you place the continuum level of the quasar, how you subtract the background, how you account for lines, absorption lines that might be confusing, might be overlapping the lines you're interested in, and how you model the velocity distribution of the gas. So all these things can be taken into account, and just to convince you that we know what we're doing, we also do this analysis completely blind. In other words, we developed the software, we analyze the spectrum without looking at the results until we judge that the best possible fit of the spectrum has been achieved. Then we let the computer tell us what the answer is and don't tweak the model any further. So, bringing together all these things, the rarity of the most suitable systems, the difficulty in the care and time it takes to record their spectra and to analyze them properly, the sum total of these sight lines, well, we could get a measurement with the correct precision, amounts to 8 cases. That's after 10 years of trying. Part of the problem is that our observation, our sample of quasar sight lines is mostly from a northern survey, the Sloan Digital Sky Survey, and the telescope that we have access to, we can apply for time to, is in the south, it's the BLT, so there's a mismatch there, and there isn't an equivalent, there wasn't until recently, an equivalent survey, a large-scale survey of the sky, comparable to Sloan, but in the south. So here's the precision sample, and there's a couple of things to remark on this. We're plotting the value on a log scale of the deuterium to hydrogen ratio as a function of the oxygen abundance here. So these 8 systems all have at less than 1/40th of solar and stretch to about 1,000th of solar. These error bars are determined in the way I've described. This is the 1 sigma and 2 sigma range about the mean value. What the first thing to point out is these 8 cases are all consistent with each other internally within the errors that we've estimated. This was not always the case. Sometimes in the past, before we did this work with the arrays, there were discordant answers that made physicists suspect that astronomers may not be very good at measuring the errors. Have you ever heard that before? But at least this is an internally consistent sample where they all agree with each other within the errors. This black line here is the chemical evolution model that accounts for the astration, the destruction of deuterium through stellar nucleosynthesis, and essentially shows that this correction is tiny compared to these errors for any of these systems, where we can take the mean value of these 8 systems, weighted mean, as the primordial abundance of deuterium. And that's the answer. The primordial abundance of deuterium is 2.51 times 10 to the minus 5, with an error which is just over 1%. And that's now much more interesting in this era of precision cosmology. In order to convert a measurement of a 1% measurement of the deuterium abundance into what we're ultimately after, which is the cosmic density of baryons, that omega baryons little h squared, we need to know these reaction rates that form and destroy deuterium and carry on to all the way to helium-4. We have to know them with comparable precision. It turns out that that was not always the case. The people who, when we looked in the literature, the knowledge of this nuclear reaction in this network here either with theory or observations was lacking, was not comparable to the astrophysical measurement. In particular, for our purpose, it is this reaction rate, the destruction of deuterium by interacting with a proton, the emission of a gamma ray to give you helium-3, and then similarly deuterium can react with another deuterium nucleus with the emission of a neutron to give you helium-3. These reactions were not well known a few years ago. It was a chance conversation with a nuclear astrophysicist. There's a meeting every 2 or 3 years called Nuclei in the Cosmos, where astrophysicists and nuclear physicists come together to exchange news and ideas. This one was the 12th in the series. It was held at Cairns on the Barrier Reef of Australia. So as you can imagine, I was very keen to go. I gave my talk and explained that this was what was holding us back to measuring omega baryons with comparable precision to the astrophysical measurement. And Carlo Gustavino, one of the nuclear astronomers, a nuclear physicist who was there, was very, pointed out, what do you mean you don't know this? And I explained the problem. And so he motivated a new measurement using the Lunar Accelerator in Italy, the laboratory underground for nuclear astrophysics. And a few years later, they produced a modern, accurate measure of that critical nuclear reaction in that network. And using, that was a major stumbling block. Now using the lunar measurement, we can convert the weighted mean of the deuterium measurement to an omega baryon. And that's the answer. As you can see, it's also 1.5% precision, the omega baryons here. This number, by the way, was deduced using the new length code to calculate all these reactions by Cara Giovanetti. Okay, so now we have this number. There's another way to get at that number, and that is using temperature and polarization fluctuations of the cosmic microwave background, which have a very precise map from the Planck satellite, and then most recently also from the Atacama Cosmology telescope. This is a familiar figure known to many of you. This is a power spectrum of the temperature fluctuations from Planck. And now we can compare omega baryons from using this method to the one that we get from BBN, from primordial nucleosynthesis. And here's the result. So the gray line here is the prediction from Planck, from CMB, and those 4, 5 color curves are the curves that describe how the abundances of helium-4, helium-3 deuterium, and lithium vary with omega baryons. Now we know omega baryons from the CMB, so we check whether our measurement agrees or otherwise with the CMB. And here's the answer. From BBN we get omega baryon little h squared 0.0224, and from the CMB we get 0.0225 with an accuracy of 1 × 10⁻⁴. And that's shown in this blow up here. Here's the CMB. Here's this curve, and that's the measurement. It's a fantastic agreement. This is the same for helium. As you can see, helium is not so sensitive to omega baryons. And here's lithium, but it shouldn't really be here. We can talk about that later if you like. Okay, so this is spectacular. Let's reflect about this for a minute. It's a spectacular agreement. In one case, we've used nuclear reactions in the first 3 minutes of the universe to give us the measure of this number. In the other case, we used the oscillations in the photon baryon fluid 400,000 years later to measure the same number. And these two pillars of the Big Bang model agree spectacularly with each other within the to accuracy. This is, in my view, a spectacular agreement, a vindication that we're on the right track with our standard model of the Big Bang. It is worth shouting from the rooftops. I don't think it's been given enough publicity. I mean, sometimes we underestimate our own achievement. We've got this model, and we hear in the news sometimes where the Big Bang model has been disproved. We never hear it's been dramatically confirmed by this comparison with these two measurements. It's not all good news, I'm afraid. Good news turns to bad, somewhat bad, when you look at what that number is of omega baryons. It's just less than 5%. And as you probably already know, the world, as we know it, galaxies, telephones, buildings, people, animals, cars, all account for less than 5% of the energy density, matter energy density of the universe. So we have a model that works perfectly up to 5%. And then there is no room in that model for the other 95% of the universe. We don't know what dark matter is. It's not in the standard model. We don't know what dark energy is. There's no room for this thing in the standard model. So is that a success or a failure? It depends how you look at it. But I find it deeply troubling. And consequently, what seems to have happened now, in my view, in this world of precision cosmology, is that we're looking for chinks in the armor of our model. One example of that is the current debate about whether H0 is 72 or 68 kilometers per second per megaparsec, depending on whether you measure it from the CMB or from nearby type 1a supernovae. People are so focused on that because maybe if that discrepancy is real, having forgotten everything that went on beforehand with the story of H0, if that discrepancy is real, then it could have some clues as the other 95% of the universe that we're missing. And similarly, people are trying to see if there is something we can tell from BBN about this. The attention, as far as BBN and other tests of this kind, the attention is focused on neutrinos. After all, so here's the assumption. So let's look again at the assumption in deriving this number of 4.8%. We've assumed GR, the Friedmann equations. They describe how the universe expands in those first 3 minutes. We looked at nuclear reaction rates, which we think we now know, not all of them, but most of them require precision. And we assume the standard model of particle physics with its components. So which doesn't include, as I said, dark matter or dark energy. So the search for something missing has focused recently on neutrinos because, after all, we now know that neutrinos have mass, and we know they can oscillate between the three different flavors. And again, there's nothing in the standard model that describes how that comes about. So as far as BBN is concerned, what people have considered is the possibility there could be a sterile neutrino, sometimes called dark radiation, an additional component to the universe that doesn't interact with matter other than through gravity, that it is right-handed as opposed to all three neutrinos being left-handed, and that if present in sufficient quantities in those first 3 minutes, will alter the expansion rate. Sometimes this additional component is incorporated into a quantity that people call the effective number of neutrino families, NF. But it really is just, what if there's an additional component to the, at those early times to the matter density of the universe? And now if you look back at this diagram and see how an additional component would affect these curves, you see here for helium, remember that everything goes into helium, all the neutrons end up into helium, so if you alter the energy balance of the energy content of the universe in the early times, and this effective number of neutrinos is rather less with 2 or more than the present value, which is a little bit more than 3 in this standard model, then you have big differences in the amount of helium. Somewhat smaller differences for deuterium, and I think it is helium-3. So maybe we can test for this using both CMB and big bang nucleosynthesis. Well, the bottom line to this is that up to now, all tests have failed to reveal a significantly different number on NF than 3.044. Here's one example. There are many more recent, there's other more recent ones, which we can look at later during the question time, if you like. This is how the deuterium to hydrogen ratio varies with an effective here. This is what the CMB gives you. The combination of the two gives you this value, which we published a few years ago now, of 3.4 plus or minus 0.45. But it's obviously there's lots of room for improvement. It's not very sensitive yet to small departures from this effective numbers on neutrinos. Okay, I'm going to give you a quick recap and mention something which we can explore a bit later about the future, where this work is going in the future. So here are the takeaway points that I would like you to take away with you. That BBN is a unique tool that allows us to probe physics in the first few minutes of the universe expansion, allows us to probe physics observationally, not theoretically, because we observe directly this primordial element abundances. Metal-poor DLAs are the best astrophysical environment for measuring the primordial abundance of deuterium, and I'm giving you three reasons for that. But here you see how easy it is to see this line, strong and well separated, and not have to account for the astration of deuterium in theoretical models. The best sample of measures of primordial deuterium has allowed us to infer the baryon density with about 1% precision. And there is a spectacular agreement with the quantity omega baryons little h squared from BBN and from the CMB taken together. Now, where do we go with this? I can show you more details on this later if you're interested. I'm coming close to my 45 minutes. Looking ahead, new instrumentation and more precise nuclear rates. I should say that that lunar experiment has been the first example. Others are going on to improve both in Europe and in China and in Japan to improve our knowledge of those other reaction rates in that diagram. So more precise nuclear reaction rate, a new instrument which will improve the statistics and bring down the precision from the 1% level to maybe a half, a third, even 0.1% level, will allow us to search better for extensions to the standard model. And these new instruments are particularly the ELT, the ESO ELT, and I can show you how that will come about. And also this instrument called CUBES, which will go towards the end of the decade on the VLT Unit 1, which opens up a new wavelength range in the ultraviolet for the measurement of deuterium. These two combined, I'm forecasting for a few years ahead, will improve the statistics very significantly, maybe down to 0.1%. And maybe that's where we're going to see the departures from the standard model. Finally, I'd like to thank Ryan and my collaborators over the last 10 or 15 years, Chad Stadell at Caltech, Regina Jorgensen when she was in Hawaii, Michael Murphy, who's in Australia, at Swinburne, and David Bowen at Princeton. And I'd like to thank you all for listening. Thank you very much.
All right, thank you for this very nice talk. Questions, especially students and postdocs to start. Let's see. It was.
Thanks. This was a really amazing talk. So at the end, we're going from 1% to 0.1%. It seems like for the neutrino problem at least, your issue is the degeneracy between ineffective and the baryon fraction. Is there another piece we need in order to break those degeneracies in addition to just making the measurements more precise, or is more precise measurement sufficient here?
Well, I think that at that point we might find differences between different light elements. So we see if still the different light elements produced by BBN give you the same answer as each other. And also the comparison with the CMB, if that continues to improve. It's just two things together that might give us the clues to what's really going on. Yeah.
How about measuring the primordial helium-3 to helium-4 abundance ratio with similar isotopic line shifts? Should I repeat?
Yeah, I didn't quite understand. Sorry.
Would it be possible to measure also the helium-3 to helium-4 abundance?
Yes.
Using isotopic
yes, we started doing that. It's very hard, but here we go. So I get some extra slides. This is something we've been investigating recently. So we can find helium-3 in absorption again in H2 region, it turns out, in Orion, in fact. It's a very weak feature. We use this upgrade to the ESO CRIRES infrared instrument to look at the 10830 line. This is work published now in 2022. So let me take you through it. And we've got other cases coming out in the near future. So this is a doublet helium-1, 1.0833 micron. These are the lines from helium-4. Somewhere in here, you can't see them in this plot, are the lines of helium-3. Now, this is just a blow-up of that region. Look at the scale. This is 1% drop. This data has signal-to-noise ratio of 1,000. But the star is bright, so you can do it, and you can get a measure of the helium-3 to helium-4 ratio this way. We've done running for one sight line so far. We have another 2 or 3 in the pipeline. So here's the result. Of course, it's done in Orion today. And helium-3 was produced in the Big Bang, and it's also consumed on the way to making helium-4, as you saw, is one other step in that process. So you have to run a galactic chemical evolution model to tell you how to go from the primordial from the observed abundance in Orion to the primordial abundance. And this is what I said at the beginning when I talked that the original deuterium measurement is not very satisfactory because there are uncertainties in this process. So this is what the BBN standard model will produce. This is our measurement here. This is one measurement. And this is what this galactic evolution model will predict for the ratio of helium-3 to helium-4. There's 10 to the minus 4 involved. So there's very much less helium-3 to helium-4 as a function of galactocentric radius. This is where we are. Now we're looking and we've found other H2 regions which are larger galactocentric radii, but there's a galactic abundance gradient. And we could be able to, if we could put another 3 or 4 points on this curve, it would definitely improve the measurement of helium-3 to helium-4. There is if I go back to my slides here, this slide here, did include helium-3 to helium-4 ratio. This is the curve we'd expect. That's the value we'd expect from the CMB. This is our current upper limit because we're not measuring it primordially. We measure it today. We know some of it. We have to make this correction. So my feeling is this is very interesting consistency measure, consistent test. I don't think we'll ever reach the same accuracy, same precision as deuterium. But let's go back 15 years or so on BBN, and if you talked to a skeptical physicist rather than an astronomer, he would tell you, well, helium-4, any number would do, because it all ends up as helium-4. Deuterium, you guys don't know how to measure errors probably because there are discordant measurements in the literature. Lithium-T doesn't agree, so does BBN really work? I think now helium is improved. Okay, still not very telling. Deuterium, as I've argued, is the one that really tells you what omega baryons is. Lithium, we could talk about that at length. The bottom line is we have not identified any astrophysical environment yet where lithium abundance is the primordial value. So I think amongst the BBN community, there's an inclination now to remove lithium from this plot because we don't know how to measure it primordially. So helium is an important consistency check, worth carrying out, but and also, of course, it can tell us about this ineffective value that I've talked about.
Thank you for the great talk. I have two questions.
Right.
First, really impressive what you can achieve with just 8 systems. I think that's really remarkable.
You have to pick the right one.
Exactly, yeah. So you highlighted this between having samples in the north, telescope access in and then you highlighted VLT, new instrument, and ELT. So you have still the same problem.
That's a really good question. We're doing the second, of course we can. So if you look back at our sample, wherever that was, let me try and recover it. We're now really going to town on this system, which is the one that has the smallest error bars, reduced them even further. And the value that I quoted is a weighted mean. So once we get an improvement by about a factor of 2, I think we can get in the precision of this measurement, it will drive all the others. So it will improve things a little bit, okay? That's very true. The mismatch between the north and the south, I think to some extent that will, I think half of the systems are in the south and half are in the north. There's not a complete exclusion zone there. SGSS goes to the declinations that you can reach with the VLT. It's just would be nice to have more in the further south. But there is a figure produced by George Becker. So the point is, this shows you the luminosity function of quasars, how many quasars there are per interval in magnitude, okay? And now that's the portion of the luminosity functions we can access with a meter-class telescope. And this is the portion we'll be able to access with a 30 to 40 meter telescope. Okay, and this is a fast rising luminosity function, several orders of magnitude. So the impact you can see in a 10 by 10 degree square of the sky. It could be 8 quasars at redshift greater than 2, which we can access with we can get high signal to noise ratio on, okay, with a VLT. Here's the same square of the sky with the ELT. Those are all quasars that in principle we could access with the same and get the same signal to noise ratio. Now, not all of those will have DLAs of the right metallicity, but you can see the huge improvement that is possible with going to an ELT. Yeah.
Hi. Also, thanks from me for the talk. I was wondering if we can somehow model the astration of deuterium in order to also use like.
I don't think I can hear you properly. Sorry.
Test. Oh.
Could you speak
Hi.
up a little bit? Sorry.
Yes. I was wondering if it's somehow possible to also model the astration of deuterium, I don't know, using like redshift dependent stellar evolution or something, to also take into account higher metallicity regions and maybe
Other
improve the
metallicity regions.
statistics. Yeah.
Yes, so people have suggested that. It's a very excellent question. And the people who produced that black line that I showed you, produced that galactic evolution model, said to us, look guys, you can go to higher metallicities because we know how to correct for that. Okay? I'm a bit hesitant. Galactic evolution models, there's so many knobs and dials. I'm sure that they know what they're doing, but are you interested in 10%, 5%, 1%? And I think at 1% it becomes a bit of a problem to trust the galactic evolution model to 1%. And so I think that to find other sidelines, it's better to either wait for the ELT or for this other instrument I mentioned, cubes. Well, that will allow us to observe deuterium down to 3,000 angstroms. In other words, access lower redshift. And again, there's many more quasars at low redshift than at high redshift. They're brighter, and their absorption spectra are less crowded with intervening other lines. And so, really, that would be a big step forward. There will be many more quasars accessible to us just if we can get down to 3,000 angstroms. And I think that's a more profitable. You have to be patient. Now there are instruments available to us now, chemical evolution models that are available now, but I think that it's worth being patient in this case and continue to strive for a sub% precision. I was waiting for Maria. The best for last.
Amazing. This is a wonderful talk, and I'm very, very happy to have such a great overview. And one thing that I would like to hear from you once again, I apologize if I've missed it, if we go back to your eta against the abundances of different species. This one.
This one here.
For instance,
sorry.
or
Coming to this one here.
Yeah, for instance. Okay. Yeah, so the blue line that you show there in the number abundance ratio against eta, and eta is here the number of baryons to the number of photons, which is like 10 to minus 9 in reality, or 7 10 to minus 9. Okay, but now the deuterium relative to hydrogen goes down.
Yeah.
So why is that? Because if the number of photons relative, if you inverse the x-axis, number of photons decreases, so the rate of photodisintegration should reduce. That means deuterium would not be reduced would not be destroyed so efficiently by radiation. So why does it go down?
Well, it's So I mean, we know the number of photons, right, from the CMB temperature, very
Okay,
accurately.
but relative. So
But the
given-
reason why
yeah.
it goes down when omega baryons increases is just that deuterium is a very fragile isotope.
Yeah.
So the more baryons, the more destruction there is, the further along the process goes to forming helium-3 and then helium-4. And
So
whereas
you mean the
helium-4 is
two-body
a very
interactions?
strong
Okay.
nuclide, so once you incorporated those neutrons to helium-4, it's very difficult to break helium-4. They're stuck in there forever, unless they find themselves inside stars. But with deuterium, it's very easy to break it. So you have more collisions, you have more the deuterium being turned into helium-3 and then helium-4, the larger the ratio of baryons to photons. Does that answer your question?
So you mean the rate of two-body interactions increases
The rate of destruction of deuterium is higher, yes.
of two-body destruction? Yeah.
Of
Yeah, but
course.
these are just two-body reactions. That doesn't show the rate of photodisintegrations. What I'm interested in is what is the cross-section of photodisintegration relative to the cross-section for this.
Oh, photodisintegration.
Yes,
Okay,
photodisintegration.
that all happens. So that all happened before. So
Okay, so the
that
temperature
all
is
happened
already too
before
low.
because
Okay.
I mean, yes, you have this destruction of deuterium. Nothing happens until the temperature has fallen enough. It's called the deuterium bottleneck. So nothing happens until the temperature and therefore the average energy of the photons is decreased enough for the BBN to actually happen. And then at that point, it is all of these reactions here are primarily these two that then destroy deuterium. And there are two-body reactions, whether deuterium or proton. So the more deuterium or protons are in the mix of baryons and photons, the more deuterium you destroy, the less is left over once all these neutrons have ended up here. Does that answer your question?
So Mark's a great journey and the quasar side, but what about the Planck side? Because as far as I know, the Planck data still contain systematics. I mean, if you see the polarization data, for instance. So I think there's also room to improve the Planck data and the data analysis and
I
to
agree.
reduce uncertainties there.
But I agree with that. But the improvement that I've seen recently is in combining, as I said, where was that plot? Let me just find it. Again, I think it's this one here. This is now combining Planck with data release 6 for the Atacama. I'm sorry, I can't. Oh, I don't know what's happening. Stop. It's combining Planck with the 6th data release for the Atacama Cosmology Telescope. This was published a few months ago in July. This is where that number on the right-hand side comes from, and it's better than just Planck by itself. People think that Planck or CMB has solved everything. I keep on being reminding people that, of course, from those power spectra, you get all of these parameters at once. They're not independent of each other. So you change one, you would change the others as well. It's internally consistent, of course, all those numbers. The people do the best job they can, but it's more complicated than just isolating omega baryon from BBN, because there all you need to know is the Hubble constant. Yeah. I don't claim to I have to take their word for it, in terms of these errors on omega baryon little h squared. I would not be able to go back to that data and work it out for myself and say, you got it wrong, you've underestimated the error. But there's very good people working on this stuff.
I don't see any more questions. Then before we thank our speaker one last time, I'll just announce there's going to be dinner, right? In 1 hour. Then let's thank our speaker again. Thank you.
Thank you for having me.